Hi friends, welcome back to the channel. Today we are going to discuss a very important topic in random vibration. It's called Miles equation. One thing which I've seen with Miles equation is that people often use it very regularly but without understanding the limitations of the equation or without really appreciating the utility of this particular equation. So in this video, I will go through what are the limitations of Miles equation, what exactly Miles equation gives you. All these things will be discussed with a very simple example. So what I have shown over here is a jet engine, and here you can see a blade had undergone a fatigue failure. Even though this equation appears very simple, please keep in mind that this equation finds a lot of applications in real life. And that's why John W. Miles invented or came up with this equation for the first time when he was working in the field of fatigue failure of aircraft equipments. So, enough of introduction. Now, let's get into what exactly Miles equation gives you. Let's consider this very simple example. Here I have a single degree of freedom system. It is subjected to base excitation. When it is subjected to base excitation, its equations of motion assume this form. Now all I am interested in is computing x for a given y. Let's say here in this form, the base moves in this fashion. So this is a time domain signal that it spans across 4 seconds. This is how the time domain signal looks like. The first thing you would tell me, hey man, this looks pretty random. Exactly, that's where the problem lies. Now your imposed or the enforced base acceleration is very random. It is not following a sinusoidal curve. Had it followed some sinusoidal behavior, it would have been easier for us. This is the acceleration on the y-axis and time on the x-axis. Then things would have been easy for us. But now what can we do when you know that your y behaves like this? What can I tell about x? What I can tell about the response that I will measure at this mass? So you can tell one thing for sure, Vivek, your input is random, so definitely the output will be also random. Good. But then what more we can tell about these things? So in the field of random vibration, we assume that there is this input, which is a real time domain signal, assumes a certain probability distribution. To drive home that point, let's look at this curve. What I have done over here is I have drawn the hope this is visible. Now I've drawn the histogram here. So what does a histogram tells? Like histogram tells the distribution of the counts in certain acceleration regime. So we can see here we can see this, most of the values are centered about 1, positive 1 and minus 1, and we can see very less number of counts are centered about 3 and minus 3. I mean around 3. So let me make it clear with this figure. Like if you see the number of counts between minus 0.139 and 0.139, there is a very large number of counts. But when you see the number of points between 2.64 and 2.92, the counts are very less. It's just 814. In other words, the particular input what we are giving is following a normal distribution with mean equal to 0. You can see the mean is 0 here. Now what else we can tell? Since the mean is 0, we can tell the variance of the signal, which is equal to the root mean square or the energy content in the signal. That also we can tell. How we can tell the root mean square? When you have a distinct pair of time and accelerations, the best way to compute RMS is like this. Like you can individually square these values, then sum it up, then divide by the number of values, then take the square root of that. then you will get the RMS value. If it is a continuous signal, even though it is not used, this is the definition for RMS value. Just keep this in mind. We are not going to use this, but strictly speaking, if x of t is a random process, then this is the equation we use to compute the RMS value. Now what we have just looked at, our input was very random, but then we told, okay, I can quantify the RMS of my input or the variance of my input. Then can I at least predict the response RMS? So my input looks like this, my output will also look like this only, but can I at least predict the RMS of the output? So that's where the whole question or the whole relevance of Miles equation comes. So Miles equation predicts the RMS response of a single degree of freedom system when it is subjected to a random base excitation, which I just showed a few minutes back. Very importantly, the base excitation should follow a white noise PSD also. So what is white noise PSD? A white noise will have the same energy content in all frequency regime. So a PSD is a plot where we will give the distribution of energy content in a signal with respect to frequency. The amplitude or the y-axis in a PSD plot is actually representing the RMS amplitude in a particular frequency regime, in a frequency range. Now if you take this particular frequency regime, then this value will be, this y-axis point will correspond to the RMS amplitude squared divided by this bandwidth. That's why it usually assumes a dimensions like this, g square per hertz. So always keep in mind this is an acceleration spectral density curve, and this g square is actually g RMS amplitude squared divided by hertz. Now let's compute the PSD of that particular time domain function which we saw just a few minutes back. That had an RMS value. It followed a normal distribution, and I told you that variance or standard deviation is same as that of the root mean square value. So for a PSD there exists another property. If you compute the area under the PSD, for in this case let's say that time domain signal, the random time domain signal, it was, this is which was a function of acceleration versus time. It was already low pass filtered to 2000 hertz. What I mean is that it had only energy contents up to 2000 hertz. All higher energy contents were not there in that system initially itself. So when you draw PSD, you have to draw it only up to 2000 hertz. Now what's the area under the curve? If m is your y-axis amplitude, then, and let's say m is in g square per hertz, then it is m in g square per hertz into 2000 and square root. Now this, what does that mean? If your RMS amplitude is 1g, then your PSD amplitude will be 0.05 g square per hertz. Okay, so this is the PSD or the power spectral density of your input signal. Okay, so we had a random input signal, then we said that it follows normal distribution, then we said that its standard deviation is same as that of the root mean square value. We computed the root mean square value, it came to 1g. This is the RMS amplitude of, this was the RMS amplitude of the signal. Then we represented the same signal in frequency domain using PSD, power spectral density, where the y-axis is the RMS amplitude squared in that particular frequency regime, is an indication of the RMS amplitude square in that particular frequency regime. Then this is the PSD corresponding to that particular input. Now shall we get an assessment about the response GRMS? That's where Miles equation comes into help. We were looking at the definition of Miles equation, and now we understand the particular input which we were talking about had a white noise PSD. That means it had energy content identically in all frequency regimes, like from 0 to 2000 hertz. It had the same energy content. The PSD was a flat line like this. If you remember correctly, PSD was like this, was looking like this, where y-axis is your frequency in hertz and your x-axis is your g square per hertz, or your RMS amplitude per hertz. This is the y-axis value. Then the area under the curve, square root of the area under the curve, was equal to your RMS amplitude, which is 1g. Now let's go to the equation. In the interest of time, I will not get into the nitty-gritties of deriving this whole equation, but let us just spend some time understanding what are the assumptions that goes into this. We assume that whatever time the curve I showed you, whatever whatever y of t versus time, that diagram, whatever I showed you, it represents a stationary random process. That means it doesn't change with time. Then it's an ergodic random process. Ergodicity means only one sample is required to quantify the whole process. Then there is no time varying stiffness and mass. I showed the classical single degree of freedom system in the first slide itself. That particular parameters, the little k and the little m, they are not varying with respect to time. And light damping, but by light damping, what I mean is the zeta will be very less, like it assumes values to the tune of 0.02 or 0.05, like 2% at damping, 5% at damping. These are the assumptions. Now comes the equation. So I have explained all this before, like my input is random, then my output is also random. I'm looking at the RMS amplitude of the signal. Then RMS amplitude of this signal is a function of this natural frequency, the zeta, and the PSD of the random input that you are giving at the base. So this is natural frequency of the system. Q is the magnification factor, which is related to damping ratio like this. And then ASD of y double dot is the, there's a PSD curve like this. This particular time domain random signal can be represented in the frequency domain as a PSD graph like this, where on the y-axis I have g square per hertz and on the x-axis I have frequency. Then if let's say this is my Fn, this is my natural frequency, then this amplitude, this is ASD, acceleration spectral density, at I could have at Fn, at natural frequency. So this value in g square per hertz, this is very important. So this value will be in g square per hertz. This is dimensionless quantity and this should be in hertz. Then it gives you the RMS amplitude of the response. How useful this equation is. So to sum up, Miles equation is a very useful equation to give or to predict the RMS amplitude of your response when your single degree of freedom system is subjected to a white noise PSD or a base excitation like this, a random base excitation like this, which follows a white noise PSD in the frequency domain. Or in other words, whatever base excitation you are giving, that particular base excitation has energy content, similar energy content across all frequencies like this. Then if you know that particular amplitude, you can plug in this Miles equation and you know your natural frequency, you know the damping in your system, then you can predict the response amplitude of your system. So this is very useful, and I would like to tell you one more thing. This was the input PSD. Now if we draw the response PSD, it will look like this. I'm not going into the details, but it will have a peak at the natural frequency. So this peak will be at Fn, natural frequency of the system. Then if you find the area under this curve, like this curve, if you find the area under this curve, let's say that curve is a response, area under that curve is a response, then root of that will be equal to x double dot RMS, what you get from Miles equation. This is also a useful thing to know. So this is your response PSD in frequency domain. In time domain, it will be again random. If you plot your x of t with respect to time, it will be going all over the places. It will be random. But then once you go into the frequency domain, it will look something like this, and RMS amplitude can be evaluated from your Miles equation. So thanks for watching. I hope that with this video you have an intuitive idea about Miles equation. What is the equation in the first place, and what are the assumptions that goes into it, and when you can use Miles equation. All these things are clearly explained in this video. I hope this video will be of very mighty help to all of you, my viewers. Thank you. Thanks for watching.